Okay, hello everyone. We are gonna continue with the modules for today. The next module is 2.1, implementing the viral infection model in CC3D, creating epithelial sheet and infection and cell type transitions. So I've posted a link in the chat for you to download the code, the model folder corresponding, the folder corresponding to this particular module, because we are gonna start working from that version to continue building up cellularizing and specializing the infection model. So in this module, we will go over how to create an epithelial cell layer, how to reference the cell type plugin in CC3D ML, how to determine the cell volume, establish how many voxels each cell occupies, and we're gonna create the cells in the Python stepper. We're gonna also talk about how do we compare the results from the cellular version to the original ODE model, and for that we will need to downscale the ODE model. We talked about we needed to rescale, how to establish the scaling between the CompuCell units and in terms of time and the Antimony model. Now we will also talk about how to rescale spatially, how to rescale the ODE spatially and establish the connection between the model and CompuCell and the CompuCell simulation domain, the size of the simulation domain. We will talk a lot about changing cell type and how do we determine the transition rules between one cell and the other based on the ODE model. We will determine what the transition probabilities are. We will show how to iterate through cells once we create them. We will talk about how to use random number generators to determine probabilities and transitions, and we will plot and compare the ODE models and the cellularized model. We will basically cellularize the epithelial cell transitions. I'll talk a little bit more about that here in a second. And at the end, if we have a little bit of time, we will talk about how to quantify the cell death mechanisms. So just a recap of what are we. So we are, what are we doing? What is the purpose of cellularizing the ODE model? And as I mentioned at the beginning of the previous section, the purpose is that ODE models hide the heterogeneity and the spatial temporal dynamics of actual biological systems. So the spatial models allow us to account and introduce the spatial aspects and the stochastic aspects associated with individual agents. And this is important because in certain diseases, the spatial temporal dynamics are important for determining the outcomes of the simulation. The module for this folder is gonna be 2.1. So in this module, as I mentioned at the beginning, we're gonna be cellularizing the processes, the transitions between cell types and the epithelial sheet. And for doing that, we have to create the epithelial sheet in the first place. And once we have the epithelial sheet, we have to somehow iterate through our cells, and for each cell determine its probability of transitioning from one cell type to the next. So that's gonna be the basic workflow. Once we have done that, once we have established the cell transitions, then we can quantify how many cells of each type we have in our CompuCell simulation, and then we can compare to the ODE models to make sure that we're tracking the results. And we will talk a little bit about what it means at the end. Again, the simulation file that we're gonna be working with is can be accessed in the link that it's in the chat, and we're specifically gonna be working with module 2.1 version 1. So you guys can upload that one to Jupyter and then make sure that it's available for you, because that's where we're gonna start. And then I'm gonna give just a couple of minutes so people can actually upload it. So we can start all at the same point. Okay, so let's just give people a couple of minutes so they can do it. Okay, so assuming that everyone has the file uploaded to Jupyter, I'm gonna go ahead and open the file. So we start with our CompuCell. We launch CompuCell in NanoHub. We start with our in player. So to open the files, we will need to launch to edit, which we can do file start to edit. Once we've launched to edit, then we can access the files by clicking CC3D project, open project. And we will have to navigate to our home directory. And once we are in our home directory, we're gonna unzip the module 2.1 version 1. Okay. Once that happens, we can come back and open the project. We click on CC3D open project, open the module 2.1 version 1, and then we open the glacier model.cc3d file. We can, in the CC3D project sidebar, if we double click on the project, that it's gonna automatically open all of the files associated with this project. And it should have the code as we finished it. Oh, I'm sorry, it's not this one. I'm sorry, it's not gonna be 2.1, the one that we're gonna launch. It's gonna be 1.0. 2.1 is the one that corresponds to, it's gonna be 1.6. 2.1 is the one that corresponds to the end of this version of this module. And it's gonna be the one that you're gonna use for the next simulation. So we go to open project, and instead of, we go to our home directory, and instead of opening 2.1, we want to open 1.0 version 0. It's gonna, in case if you haven't unzipped it from the previous module, you can unzip it now. And we open the CC3D file. It's gonna be, now we're gonna have the module 1.6 version 0 uploaded. And this is the code as we finished last time in the previous section, in the previous module. We're plotting, we basically added the plots for the antimony model that we loaded in CompuCell. Okay. Just gonna give everyone a minute to open the file. I would like people to follow along as we construct this model. Okay, assuming that everyone has it open, we are gonna start at the XML, in the XML document, and we can see that this this particular version does not has the cell death, the dead cells. So what I'm gonna go ahead and do is that I'm gonna add them manually. Because I'm gonna need the cell transition into cell. So I can copy this snippet from here. And now I have the same snippet as the one above. Now I change it so I can add a different cell type. So, and this is adding cell types manually. So this is gonna be frozen as well because it's gonna be the dead cells, but we're gonna add them manually instead of using wizard. And that's it. It's that simple. I remember there was questions in the previous module. What do we do if we did not include cells? This is if you haven't attributed lots of properties to cell. This is just an easy way to manually add cells to the XML file. Okay. So I mentioned in the previous module that this specification defines the cell type available to the user, the cell types that each cell can adopt, but it doesn't specify it doesn't create specific cells. To do that, we're gonna, I showed that the blob initializer in the previous version, in the previous module, can create cells automatically, but we're not gonna be using that. That's why it's deleted in this version. We're just gonna add them manually in the steppable file, in the Python steppable files. Make sure that I save this so I have the dead cells available. Now, just a refresher of the conversion factors. The conversion factors define what the scales of my simulation are in terms of real-time, real world units. We, in these conversion factors, we specified earlier that the cell diameter is gonna be 5, which means that the cell width is 5 voxels, and the cell volume is gonna be 5 by 5, so we have a squared cell occupying 20. Each cell is gonna be squared and occupy 20 voxels when we create them. So the idea, as TJ showed in his presentation of the COVID model, is that we want to create this layer of epithelial cell that is going to provide the quasi 2D simulation domain for our epithelium. And we wanted to put it in the lower level, on the lower level of our simulation, so we can then eventually add immune cells and chemical fields on the upper levels. The simulation, the dimensions of my simulation, we specified in using Wizard, but they are also accessible in the XML file inside the pods category in the dimensions entry. And we could also manipulate the dimensions of our simulation here if we wanted to. But the idea is that we will try to use the Python stepable to create a epithelium that looks like the one here in the figure. So the idea, conceptually, what we want to do, let's assume that this is our simulation domain. What we want to do is that we want to iterate through the voxels of our domain, and based on the cell width and the cell volume, locate cells in the simulation domain. So, for example, let's say this is my x-axis and this is my y-axis, and then I am in the lower level. So I set for this particular example, I set the width of the cell to be 2. So I iterate through my lattice or my simulation domains in steps of 2 voxels. And I also do it in the y dimension. So I do it in the x dimension and I do it in the y dimension. And as I iterate through the dimension, then I create cells and locate them in the simulation domain. So here I create one, is the identifier of a cell. So the cell occupies 4 voxels, but it's the same cell. It just occupies multiple voxels. And then I continue iterating through my simulation domain. So I start creating different cells. So I reach the end of the Y domain. So now I move up on my X domain by a step of the size of the cell dimension, and then create cell in the next available spot. Okay, and this is important because this is what we're gonna, this is what the code that we're gonna generate is gonna be doing. So this is just conceptually what we need to do if we wanna define and create an epithelial cell layer. And here we created 9 cells, each cell occupying 4 voxels. So how do we do this? So the idea is that we're gonna have to iterate through the entire domain, and as I mentioned, we'll have to iterate sequentially in the X dimension and the Y dimension. And then as we iterate through the simulation domain, then we're gonna have to do something that is gonna be provided by the Python library to create a cell at that particular location in the simulation domain. This is just a quick reminder of what iterators are in Python. The iterator iterates through a list, through the objects of a list, and then inside that, the iterator is a for loop, and inside that for loop, then we can do stuff to the objects of that list. With respect to our simulation, there is a property of the simulation that it's called the self.dim that gives you the dimension of the simulation in the specific domain that you want. So for example, self.dim.x gives you the dimensions of the simulation in the X dimension. Self.dim.y gives you the simulation, the length of your simulation, the dimension of your simulation in the Y dimension. And same with Z. Z will give you in the Z dimension. So when we use range, zero is the start time, the start point. Self.dim.x is the last point. And then we said previously that we're gonna step through it in steps equal to, it's the cell diameter, right? It's not the cell area or the cell volume. And I explained previously that we use volume loosely here to refer to the number of voxels that a particular cell occupies, even if it's in a two-dimensional space. So for example, for this particular simulation, when I say range from 0 to self.dim.x cell diameter, that is equivalent to say I am creating a list that goes from range 0 to 200 in steps of 5, because 5 is the number that we specify as the cell diameter. So that's gonna generate a list of numbers, in this particular case, that goes by steps of 5. And these are the numbers that we're gonna use to point at specific locations in the simulation domain. So, so we will start doing that. We'll have to code it ourselves because this is mostly Python coding. So we're gonna we wanna do it in our, as we mentioned earlier, the steppable class has 4 different functions. The start function is a function that runs before the simulation starts, before the first step in the simulation. And that is where we want to create our epithelial cheat, because that's what's gonna provide the cells to the domain. So we're gonna do it here before the, we can do it here at the top of our start function. What we're gonna do is that we're gonna use the Python iterator, and we're gonna iterate in the X dimension. That X can be whatever we want. It's just a convenience variable that it's gonna change value as we iterate through the list. And we can use the code that I specified before, that I explained before. So as I explained earlier, this is gonna create a list that goes from 0 to 200 on steps of 5. And as I showed with my small animation, now we also wanna iterate in the Y dimension. Since our cells are squared, we're gonna use the same list. They don't have to, right? We could have different steps in different dimensions and then have cells not be square. Okay, so this loop now is looping through the numbers that correspond to locations in my simulation domain, right? So what I do want to do now is, once I have this iteration, I want to be able to create cells and starting at those particular positions. So we do have a convenience function for a convenient snippet code for it in CC3D Python. And again, the reason we use CC3D Python is because those are the snippets associated with the steppable Python file. If we were in XML, we will use CC3D ML. So now this is the pull down menu. What we want to do now is that we want to create cells. And that one in particular can be accessed in cell manipulation. Cell manipulation gives us multiple options for creating cells, for manipulating cells. We can delete cell, get the ID, look at what cell is at a particular location, etc. But what we want to do is we want to create cell inside this loop. Okay. So again, I get my template code, and now I have to modify the template code to make it specific to my particular simulation. This template code is gonna include, let me walk you through what the template code includes. The template includes the solve that new cell method. That basically is creating a cell object. So the cell is being initialized. It still doesn't have a location, but it's already created. It has generated an ID for it, and I must specify what is the cell type that I want to associate with my cell. Since I want to start with all my cells uninfected, I need to change the type to uninfected. And note, and this is very important, that the way cell types are associated, are referenced in the Python steppable file is as it's all caps. It's always gonna be, that's always gonna be the case. So as I mentioned, this particular part of the code creates the cell. It gives it an ID. It creates the object as a cell as an object. It gives it an ID and a type. But now we have to put this cell somewhere, and the code to do that is cell underscore field. And what we're gonna do there is that basically we're gonna specify what location we want our cell to be at. And again, that is what the X and Y variables are for, because those X and Y variables are iterating through different locations of my simulation domain. So X is I'm gonna delete this because I'm already getting these values from my iterator. I'm gonna delete this because I already have the size that I wanna step through, which is my cell diameter. So now I'm gonna say that I'm gonna put a cell at location X, or from location X to location X plus cell underscore diameter. So it's basically creating in the X dimension a cell that goes from X to X plus cell diameter. This number has to be an integer for it to work. I do the same in the Y dimension. I go from Y to Y plus the integer of the cell diameter. And I specify, and then the what layer I want to put my in the C dimension, I can specify here. Note that if I just say, if I don't specify a range, if I don't say from Y to Y plus something, if I just give one number, it's just gonna create a one layer. It's gonna create, it's gonna be one voxel in that particular layer, which is what we want to be able to create the epithelial layer. Okay, you guys, right? And then now we can save the simulation, and then come back to our CompuCell, and we can execute it. Okay. Yeah, it crashed on me. Did anyone else experience that same problem? I'm gonna relaunch it here in a second. Has everyone been able to work up to this point? So if your computer crashes, you just have to relaunch it, launch to edit again. I'm not sure whether if recent projects works on NanoHub. Nope. So okay. So the error seems to be on my end. So we open, we go to, oh yeah, I'm sorry, right. It was my mistake. That when in the range, when you specify in the for loop, when you specify the step size, that one has to be an integer as well. I just let it as a float, but it does has to be an integer. So if you guys can see my screen, I'm gonna correct that. Okay. So in my for loop, when I specify the step here, it needs to be an integer as well. These are some of the small details that it's important to keep in mind, but we often encounter them and we just go back, fix them. So now when I launch CompuCell, I can come to my graphic window, choose the cell field, and if I am in layer 1, I'm not gonna see anything because I haven't located anything in layer 1. But if I don't go down to layer 0, to level 0, which is 0 on the C dimension, then I should be able to see my cells. And I wanna make sure that people got their cells as well. Let me see if I can. Okay, people who got the error, I hope they were able to fix it. So now we have created our epithelial cells. If we were to display it in 3D, we should be able to see the layer just as in the image that I just showed before, right? So we have a layer that is 1 voxel thick in the C dimension and contains all of my cells. I'll just give people a couple of minutes. So one recommendation that I would give is that you can actually open both the version of the code that corresponds to this module and the version of the code that corresponds to the next module, the one that I accidentally opened at the beginning. And then if you're running into issues, then you can actually reference that one, because that one is gonna have all of the steps that we're gonna be working on this one, such that you can compare the versions. And then if you have a error in your code, then you can identify it that way. Okay, let's continue with the exercise. Now that we have our epithelial cell sheet, I just walk you through how to display the cell field, right? We execute our code in CompuCell. I just hit step, so it's not actually simulating anything. If I were to hit play, it will start plotting the data from the ODE. But what I wanted to be able to see was that I was creating the epithelial layer correctly. Okay, so now that we have created cells, we do have a number of cells in our simulation domain because we have specified their size and we have located them. And actually, if we look at the console, it tells you how many cells you have in your simulation domain at a particular time. So we have 1,600 cells in this particular simulation. So now we need to, the general idea is that we're gonna use the ODE model to determine how these cells transition from uninfected to infected, from infected to virus releasing, and from virus releasing to death. We're gonna use the parameters of the ODE model and the rate equations to determine those transition probabilities. But to be able to determine those transitions probabilities, I need to scale down the ODE model so it corresponds to the same size of the simulation domain. And that would also allow me to compare the results from the simulation from the ODE model to the CompuCell simulation. So for example, in the original ODE model, you guys play with, we explored that T0 parameter that specify how many target cells your ODE model starts with. In that ODE model, the number was 10 to, I think it was 1.0 e to the 7, 10 million. Whereas here we have 1,600. So we have a very small number of cells relative to the ODE model. So to be able to compare those, we'll have to make our ODE model sort of like a short version of the original ODE model. And also parameters are gonna be rescaled too by the MCS to days conversion that we discussed at the very beginning of the previous section. So for that, what we're gonna do is that we're gonna create convenient scaling factors that are gonna allow us to rescale the size of the outputs of the ODEs to the size of the simulation that we are doing, the size of the simulation domain that we have in terms of number of cells. To do that, we're gonna go to our steppable function, and we're gonna go into our init function, because again, these are gonna be parameters that are gonna be available throughout we want to make available throughout the step class, the steppable class. And we're gonna call them scaling coefficients. The first scaling coefficient is gonna be the scale by volume coefficient. Basically, we have to make we're gonna assume that the ODE model is a bigger volume than the one that we are representing here. And then we're gonna have to scale it down. But for now, we're gonna set it to 0 or to none. the scale by voxel allows us to scale quantities, although we're not going to be using this extensively for now, allow us to scale quantities by the number of voxels that each cell occupies. We're not going to go into right now. It's something that is going to be covered later on. But the other one that we do need is the scale by time, because we're going to need to also rescale the parameters of the model in terms of not just spatial units, but also time units. So we just created those variables and set them to none in the init function. The next step is for us to actually rescale the outputs of the, I'm sorry, we need to actually specify what these scaling factors will be. We're gonna do that in the start function, and we need them after we create cells, because as I've mentioned, the number of cells is gonna be the rescaling factor, the number that we're gonna rescale, the number that we're gonna use to rescale by volume. So we're gonna paste the same variables inside the start function, and then we're not gonna discuss a lot of the details of what the rescaling factors mean. Just one second. We're not gonna discuss how are we determining, we're not gonna discuss a lot how we're determining these scaling factors, but it's important to conceptually understand what is that we are trying to do here. We're basically downsizing the ODE model so we can convert it to our cellular version. The first, we need that the number of cells that we have in the simulations is 1600, but there is another way to quantify, and I will talk about it later, but another way of quantifying the number of cells that I have in my simulation is by measuring the length of the cell list. What I'm gonna do now, because I haven't introduced the idea yet, is I'm just gonna say, I'm gonna enter manually. So I know that I have 1600 cells. And then my rescaling factor by volume is gonna be my number of cells in CompuCell over the number of cells in the ODE model. And we practiced in the previous section, in the previous module, how to reference those values by referencing the dictionary associated with the module. And I mentioned that this is a particular type of syntax, and that's why I can type it from my mind. If you do not know it, you can come to Python, SVML solver, get value for free floating model. For free floating, get SVML value for free floating model. And that will give you the snippet to fill up to get the specific value. The specific value that we want from the ODE is the T0 value. So now we're rescaling. This scaling factor will allow us to rescale everything in terms of the number of cells that I have in my simulation. I'm gonna I'm gonna leave this one to none because we're not gonna use it for now. The scale by time is the same scale that I've been using constantly. Is the conversion factor between days, between the CompuSol units, the Monte Carlo step to days. And I forgot to mention previously that we do expect to have a lecture where we're gonna explain the inner workings of CompuSol and where those, what defines a Monte Carlo step. For now, we're just gonna assume that it's just one simulation step. Okay, now that we have defined this scaling factors, now I can go and rescale the outputs to my plot windows such that I can basically scale down the ODE model to the size of my simulation domain. And it's gonna be the one that rescales that is, oops, sorry, rescale by volume. So I basically have to come to every place where I am plotting values from the, let's do it so it becomes more apparent. Let's do it where everywhere where I'm calling values from the ODE model, I'm gonna rescale by this factor. Which is when I count the amount of virus, when I count the amount of cytokine, when I count the amount of APCs, when I count the number of effector cells in the lymph node, the effector cells in the tissue, the number of dead cells, the number of I2 cells, the number of I1 cells, and the number of uninfected cells. And then it becomes very obvious here, right? Because when T equals T0, this number is gonna be 1600, which is what we wanted. Okay. If we save and go back to CompuSol and we execute the model again, just one second. Just one second. I might have accidentally deleted it. Yeah. Okay, so the model is appropriately loaded. Okay. So the problem is that I am trying to call the scaling factors before loading the model. So the good practice. So the ODE model here, this ODE model dictionary has not been initialized yet. So I need to specify those rescaling factors after I load my Antimony model. Okay. So now when we look before, when we were launching, this is now the solutions to the ODE model. But before, this number was 10 to the 7, right? But now it's 1600 because we have scaled down the outputs of the ODE model such that we can now compare, because we have the same number of cells in the ODE model as in the output, in the output of the ODE model as in the simulation, in the complete cell simulation. Okay, so I'm just gonna give everyone a second so they can do those rescalings by themselves. Okay, so that was just prep work so we can start comparing our simulation results. So we rescaled, and when we compare before rescaling was 10 to the 7, and now after rescaling is 1600, which is the same number of cells that I have at the beginning of my simulation. Okay, so just I need to take a 5-minute break, and I'll be back here in 5 minutes, and then we can start talking about how to translate the ODs to transition rules for cells. Okay, we're back. What we have done so far by rescaling the ODE model is prep work so we can now start comparing the actual simulation results once we start implementing changes in cell type. This rescaling will allow us to compare CC3D simulation outputs to the ODE outputs. What we need to understand is how to do that translation. And I've been mentioning a couple of times that the way we do that translation is by taking the rate equations of the antimony model as describing some transition probability. In these rates in the ODE model are really describing the rates of change of populations of cells, how the number of uninfected cells is changing in time. What is the slope of this curve? How the number of infected cells is changing in types, and the slope is described by the ODEs. So the idea is that now we're gonna take those rate equations and turn them that refer to populations, and we're gonna translate them into something that refers to individual agents. And this part is critical because this is where the translation, the cellularization of the model is gonna come from. The general idea is that we will use the parameters of the antimony model to calculate a transition probability for each individual cell depending on the cell type they belong to. And we do that by assuming that the probability of transition follows a Poisson distribution, which is basically the equation that is shown here. We're not gonna get deep into the math, just show how to translate one to the other. For an event of instantaneous probability per unit, that has an instantaneous probability per unit time, TR, the probability of at least one occurrence of such event is gonna be determined by 1 minus E to the minus TR, if that's a typo here, that times the time step. So if the time step is larger, the probability becomes closer to 1. And this is the rule of the transition interest, of the compound interest. But the idea is that TR is the parameter that we're gonna define, is a variable that we're gonna infer from or determine from the rate parameters in the ODE equation. Right, and that's gonna be determined by the parameters in the model. I think I've said it a couple of times. So, okay, this is the fun part. Now we're gonna start implementing transition between cell types. The first transition rule that the first transition rule that we're going to be talking about is the transition from uninfected to infected. And we saw when we were talking about that model in James's module, that the transition, that the rate of change is given by B beta VT, where beta is the infectivity parameter, B is the amount of virus, and then T represents the number of uninfected cells. So if we drop the number of uninfected cells, right, because we're gonna iterate through individual uninfected cells, the probability is gonna, the probability rate per uninfected cell is B times beta times B. And all we need to do now is define the probability of transitioning from uninfected to infected for an individual cell to be 1 minus the exponent minus beta times V. And that is the equation that we're gonna use to determine the probability, the transition probability between cell types in CompuCell. There is a caveat here that is very important too, and it's gonna become important later on, that when we determine V is a variable of the model, but we will use V from the ODE, from the Antimony model, to determine the transition probability in CompuCell, because we do not have virus in CompuCell yet. So we need to get that value from somewhere, and we will get it from our Antimony model. And that is what we call the cellularized model being slaved to the ODE model. Because the initial transition, the transition between uninfected to infected, is determined by the amount of virus in the ODE system. Later on, we will break that loop, break that dependency of the cellularized model on the Antimony model, and then have cells actually secrete and get infected by virus in the CompuCell model, the cellular model. It's also important to keep the cellular model slaved to the ODE model, just to make sure that our variables are tracking. But philosophically, what this means, or what this entails, is that we are incorporating the assumption that every cell is equally susceptible to get infected by virus as every other cell, uninfected cell. So we are not adding any special considerations since every cell is equally probable to get infected. So the general rule to establish these transition rules will be to iterate through the cells of a particular type. Then once we are iterating the same way we iterated through the cellular domain, the simulation domain, now we're gonna iterate through over our cells, and then we're gonna determine the probability of transitioning for each individual cell. Once we have determined that transition probability, we're gonna roll a dice, or in technical terms, we're gonna generate a random number that we're gonna use to determine whether that cell transitions or not. And then if the cell transitions, when that condition is met, we haven't talked about the condition, but when the condition is met, we will change the cell type from uninfected to infected. So, and this general workflow is gonna apply for all the transitions that we're gonna be working on today. Not necessarily all of the, not necessarily every transition in CompuCell has to be in this way, but these particular transitions that we're gonna be working on are gonna be determined this way. So how do we iterate through cells in CompuCell? So CC3D, as I mentioned earlier in the previous module, CC3D has CC3D includes convenient snippet codes that allow you to iterate through or over different simulation objects. If we can have access to those snippets by going to CC3D Python, intuit it, going to CC3D Python, visit, and then we get multiple options of what objects we can iterate over. We can iterate over all of the cells in our simulation. We can iterate over all cells of a given cell type. We haven't talked about any of this, but we can iterate over all the pixels or voxels in my simulation domain. And we will talk about some of these later, but these are the ones that apply to the concepts that we have introduced so far. So the way CompuSol does that is in terms of iterating over cells, is that CompuSol has a concept of a cell list, and the cell list is a Python list that contains pointers to individual cells in the simulation. And there's two types of cell lists that we use constantly. The self.cell list, that is a Python list that contains pointers to all of the cells in the simulation. And we have the cell list by type, and then it takes a type as an input that contains a pointer to all the cells of a given type determined by the inputs to the method. For example, if I wanna iterate through the cell list by the type uninfected, then I can go over the list. Oh, I can access the list by using the syntax self.list by type self uninfected as an input. So that's gonna generate the list of cell types, uninfected cell types. Again, note that cell types are always referenced as in all caps. So the idea is that then we can combine the Python iterator with the cell list to be able to iterate through the cells, either all the cells in the simulation or cells by specific types. Okay, so we're gonna start working on it. The first thing we need to do is we have to establish the transition between uninfected to infected cells, is that we need to iterate over our uninfected cells. So we're gonna go to a step function. We're gonna do it before integrating our ODEs. And then we're gonna use the Python snippet, the tweeted snippet from visit, CC3D Python visit, all cells of a given type. And we want to iterate over the cells, the uninfected cells. So we have to adapt the code to iterate over the uninfected cells. We can delete the comments associated with it. So now we're iterating through our uninfected cells, and we need to do something to them. Right, so we iterate and we do something to them. what we do inside the loop is gonna be done to the specific cell that is pointed at with this variable. So this variable is pointing at individual cells inside the cell list by type list. Now we can calculate the probability of transitioning for each individual cell. So for doing that, we're gonna define a variable called infection rate. And we discussed earlier that the infection rate is determined by the parameters of the ODE model that are beta and V, the virus. So what we're gonna do is that we're going to reference those values. Again, this use is very frequent, so we can, if you have familiarity with it, you can already type it. Otherwise, it's always available in CC3D Python, SBML solver, get SBML value for free floating. So what we want is the parameter beta, and we want the value of B. I'm sorry. So that's gonna determine our infection rate. Now once we have the infection rate, we can calculate the transition probability for each cell, and that is we need to create another variable called PR infect, and that is gonna be the Poisson distribution that we talked about. We're gonna use the exponent we're gonna use from the math library that we imported at the very beginning. And it's gonna be effect rate. Okay, now these parameters, when I import them, they are still given in terms of the size of and the timescales of the original ODE. So I need to translate them both to the side of my simulation domain and my my simulation domain and my Monte Carlo test unit. So the conversion factor will be this one second. The convection factor will be the cell scale by volume. How to rescale these parameters? It's not this one, I'm sorry, it's gonna be beta. How to rescale these parameters is not necessarily super intuitive. Actually, TJ is actually working on publishing this method. So we're gonna rescale beta by the volume. It's not, it's by. So we're just gonna tell you how to rescale the parameters. If you're interested in understanding which parameters get rescaled by what, I think TJ is the person that you want to contact. But it is really important because that is going to determine that you get the right transition probabilities. But we're not going to get deep into the math of it behind it. So we're just going to tell you now here which are the scaling factors that you need to use to determine the scaling probabilities. So now this is going to be beta here. Okay. So now we have the probability of infection. Our workflow was 1, iterate through the cells of a given type. 2nd, determine what the transition probability is. The 3rd step is to roll a dice to compare to my to the transition probability. And the way I roll a dice in Python is by using a random number generator, and that's why there is an option of importing random number generators from NumPy, but we have already also imported the library random, and we will use that library to generate a random number. This function random.random generates the a random number between 0 and 1. Yeah, right. Thank you for pointing that out, Katie. So now we have determined the probability of infection. Now we roll the dice by generating a random number, and then we need to compare these two, right, to determine whether the transition is going to happen or not. And the way we do that is that we establish a conditional if the random number is smaller than the probability of infection, then the cell is going to transition type. Why it's smaller than? Suppose that the transition probability is super small. It's a small number. So the cell, that PR, that underscore infect is small. Most of the time when you generate this number, that number is going to be much bigger than the infection probability, the probability of infection. But once in a while, it might generate a number that is smaller, and that is the case. That is the event that you that will trigger a transition. So that's why it's the random number. It's smaller than the transition probability. So yeah, some people seem to be interested in learning more about how to rescale the parameters and stuff. That's good. So yeah, now we have determined the transition rate, the transition probability. We have rolled the dice. Basically, this line 141 here, it's rolling the dice. And if this condition is met, then we want to change the cell type from uninfected to infected. Otherwise, nothing happens. So how do we do that? So if the transition occurs, right, we will change the type of the particular cell that we're iterating over. And in that case, we want to manipulate the cell type, the type of the particular cell. And CompuCell in the CC3D Python, tweeted in the CC3D Python pull-down menu, has an option called cell attributes. And there is a lot of cell attributes associated that we can pull and we can reference with predefined codes, template codes. But the one that we're interested in is the cell type. So the reference to the cell type is gonna be cell dot type. Why cell dot type? And we don't well, why is cell dot type? Because cell is the variable that we're using to iterate or over the list of uninfected cells. So cell is a variable that indicates, it points to an individual cell. And that type specified an attribute of that cell, meaning the cell's type. And this we have both read and write access, which means that we can define a variable in terms of the type of the cell, but we can also define the type of the cell. So we can write the type of the cell, and that's what we want to do. We want to, if the condition is met, we want to override the type of the cell, which is in this case is uninfected. And as I mentioned before, cell types are referenced by capstones, by all caps. So with this particular syntax, we can redefine the type of a particular cell. Okay. Right. So this finishes the workflow that I pointed out at the beginning of when I started discussing the transition rules. So what we're gonna do now is we're gonna execute CompuSol to make sure that our code is working. Okay, and there's nothing changed yet, but when we look at the number of uninfected cells, they haven't changed either in the ODE model. So that is not a real cell type. The real cell type is infected. So that indicated that the loop go through. So it got to a point where there was a transition was going to happen, but I hadn't defined this pause here. But I hadn't defined a particular valid cell type. So now we can see that there was one cell that transitioned from uninfected to infected, and as we expect, because of how this curve behaves, we should see more cells getting infected, and eventually all of them are going to get infected. But we haven't established any other transition rules. So our cells, our CompuSol cells are going just from uninfected to infected. So now we know that the infection is happening, but now we need to measure whether we are getting the right infection rate, whether we are tracking the way this blue curve behaves, whether we are actually tracking the way this blue curve behaves. So to do that, we are gonna go back to plots, and we're gonna add another data series that is gonna overlay in this population data window, so that we can actually compare the number of uninfected cells in the ODE versus the number of uninfected cells in the CompuSol simulation. Okay. Let's do that. It gets exciting when it works out. So from the previous model, we already know how to add a data series, and we want to add it in the population data window. What we're gonna do is we're gonna basically copy the snippet corresponding to the uninfected cells in the ODE, because that has the correct handle. We're gonna eliminate ODE. Instead of lines, to be able to distinguish them, we're gonna use dots in this case. So lines are gonna refer to the ODEs, dots are gonna refer to the cellular version of the model. And then it's not gonna be line size, it's gonna be dot size. And we're gonna set that one to 5. Okay, so now we added another series to the population data window, so we can track the number of uninfected cells in the simulation. Right, and this is a quick refresher. We create the plot window, we had it already in the start function, we add the data series, and now we have to add the points, the data points in the step function. For the data plot, for the data plots, so to be able to add the data plots, the data points, I need to be able to count how many uninfected cells I have in my simulation. And conveniently, I can do that by actually measuring the length of the list of uninfected cells. Because as I mentioned earlier, this contains pointers to all of the uninfected cells in my simulation. So if I count the number of pointers that I have, then I can count the number of uninfected cells that I have. I'm just trying to stay as closely as the code that we generated for you. So just making sure that I use the right number, the right variable name, right? So what we're gonna do is that we're gonna store that number, which is the length of the cell list, in a variable called num cells uninfected. So now this number is the number of cells uninfected in my simulation, or uninfected cells in my simulation. So now I add the, now that I have counted, all I need to add is the data point. Again, I can come to CC3D Python, scientific plots, add data point. These are the familiar templates. I have to reference the right handle, which is pub_data window. I have to reference the right data series that I'm calling uninfected. I have to rescale my time so I can display in terms of days and not Monte Carlo steps. And now I can plot the number of cells uninfected, so I'm going to be able to see the number of cells uninfected at each time. Okay, so I'm going to do something just for comparison purposes. I'm going to turn off when I'm plotting the number of all cells are not the uninfected cells from the ODE. And this is just so I can track whether these equations are tracking or not. The way I do that is I can just, in the part of the code where I'm adding the data points corresponding to the ODE model, I can just block comment that. And now the code is still available to me, but it's not gonna do anything because I commented out. Okay, now I can save the simulation. I can go back to CompuCell. So now we are comparing the number of uninfected cells to the ODE and the model. So I got a question for you guys. Maybe you can answer on the chat. What is this difference coming from? Any ideas? Up until now, we have 1,600 uninfected cells in CompuCell, but we have 1,599, right? And the reason that difference is, the reason we're getting that difference is because in CompuCell, when the number of cells is a discrete number, right? We have 1 cell, 2 cells, 3 cells, 4 cells, 5 cells, right? So we cannot have a half of a cell infected. It has to be the cell is either infected or not infected. So in this case, the ODE model is continuous, it's not discrete. So the number of uninfected cells can be a fraction or a number between between integer numbers. So what I do expect though is now we can see that as one cell transition from uninfected to infected, the number of uninfected cells in the CompuCell model dropped from 600 to 1,599, whereas the ODE model keeps decreasing continuously, whereas this one is jumping down in discrete steps. What's going to happen is that as more and more cells get infected, we expect our curves to look much similar to each other. And we can see how the compusol curve, which is the dots curve, is exactly on top of the OD curve, that is the solid line. Okay. So I'm gonna wait for people to catch up, because we're gonna repeat this process to go from uninfected to infected cells. Okay, so so what we will do is that we will repeat the process for the transition from infected to virus releasing. And I hope that the going through the process again sort of clarifies how the transitions are being determined. Okay, so we can go back to the code to try it. So now the transition rule from infected to virus releasing. So now we're gonna implement the second transition. We have implemented the transition from uninfected to early infected, and then the transition, now we're gonna implement the transition from early infected to virus releasing. So again, we are gonna use the rate equations to determine what the probability of transitioning is between cell types. So in the ODE model, the transition from T to I1 is determined by K times I1. So in this case, our probability or transition rate is determined by K. So K is gonna be the parameter that we're gonna use to calculate the transition probability between cell types. K, as we remember, is the inverse, is a parameter that controls how much time the cell spends in the clip phase. After getting infected, how much time the cell spends in infected but not releasing virus. So we're gonna so based on this on the rate equation, we can determine that the probability of transition from infected to virus releasing is gonna be 1 minus E to the minus K times delta T. So again, we have to follow the same workflow. The workflow is to iterate through cells by their type. In this case, it's gonna be by the infected type. We're gonna calculate the transition probability. And after we calculate the transition probability, we're gonna roll the dice, and we're gonna, based on the outcomes of rolling the dice, we will determine whether the cell transitions from early to late infected, or in this case, from infected to virus releasing. Okay, and I'm gonna go slow on this one, so make sure that everyone can follow. So I end the Python steppable. I go to my start function, and before implementing the transition from uninfected to infected, we're gonna implement the transition from infected to virus releasing. Oh, I'm sorry, this is a start function. It's in the, we need this in the step function. I'm gonna cut this. I'm gonna go to my step function, and it's the same. Okay. So again, from the beginning, the first thing we need to do is to iterate through cells, through all the cells that belong to the infected type. So to iterate through the cells, we go to CC3D Python, intuit it, visit all cells of a given type, Now, this time we're gonna iterate through the infected cells instead of the uninfected cells. And again, we do something, we iterate through the cell, and we do something inside to the cell list, and we do something inside of them. What do we do inside? The first thing is we calculate the probability of transition. To calculate that probability of transitioning, we're gonna create a variable called I'm gonna call it eclipse trace in this case. And this one is gonna be given by K, as discussed in the slides here. K is a parameter of the SBMM model. So to reference the SBMM model, I go to CC3D Python, SBML solver, get SVML value for free-floating model. And that provides the snippet that I need to access the value on the Antimony model. We named this Antimony model ODE model. And the parameter that we care about here is gonna be K. And this one needs rescaling also by this scale by time scaling factor. Again, if you're interested in learning when to use the different scale factors, I would encourage you to reach out to TJ. Now we're gonna call this the probability of going to releasing. And that one is gonna be given by the Poisson distribution as specified here. Gonna be 1 minus, to use exponent, we can use the library, the math library, math.x, x refers to the exponent, minus this rate. And with that, we have determined the probability of releasing. The next step in the workflow is to roll the dice to compare this probability to a random number. So the way we do that is that we use the if, the conditional, Python conditional if, and the library random, that, as we explained earlier, this function generates a random number between 0 and 1. And we also explained that this number has to be smaller than the probability of transitioning to releasing. Okay, so again, just to recap, iterate through the cell, determine the transition probability using the Poisson distribution, roll the dice, compare the probability of transitioning to a random number, and if the condition is met, then we change the number. We shall change the type of the cell. And as we discussed earlier, the way we can access the cell attributes is by going to the pull-down menu, CC3D Python, access the cell attributes, and among all of the cell attributes that we haven't talked about, the only one we care about in this particular case is the cell type. And again, here is a reminder that you can use this for read and write purposes. In this particular case, it's been read because this variable is being defined in terms of the cell type, but we want to write, we want to override this particular cells, the cell that we're iterating through, we want to change its type. So this time, if the cell belongs the cell that we're iterating through in the infected cell list, if all of the conditions are met, then that cell is gonna become virus releasing. Okay, and we know that we need to be able to quantify and compare the data plots. So we added the number of uninfected cells in the population data, in the population window, in the cell population window, population data window. We overlaid it on top of the number of uninfected cells in the ODE. What we're gonna do now is that we're gonna do the same, but for the number of infected cells. Why the number of infected cells? Because we have determined so far all of the transitions that are possible for uninfected cells and for infected cells. We cannot plot the virus releasing yet because we will have to also define the transition probability for those from virus releasing to death. And just to stick to the original code, the color that it shows for this particular one was red. And we're gonna be using dots. Okay. Now we can come back to the step function, and the same way that we quantify how many infected cells I have in the simulation, uninfected cells I had in the simulation, I can do the same to count the number of infected cells. And then when I do that, the way I do that is I measure the length of the list by type. And in this particular case, it will be the cell list by type infected, because that is gonna tell me how many infected cells I have in my simulation. So what I'm gonna do is I'm gonna copy the code, because I can use it as a template, just as I'm using the other, the CC3D Python templates. I can use previous code as template. I have, and now it's gonna be the number of cells infected, and it's gonna, the list that I wanna measure is gonna be the cell list by type infected. As the length is gonna tell me how many cells I have of that particular type. Now I can add, then in the following the plotting workflow, I can add a data point to my, I can add a data point to my infected cities that I just created in the start function. And now it's gonna be the number of infected cells instead. So again, quick recap. We iterated through the number of infected cells. We calculated the transition probability between them. We rolled the dice and decided that if the condition is met, the cell changes its type. And then to be able to compare the ODE results and the cellular version results, we can we add a data series to our population data window called infected. And then after adding that data series, we can add data points to the series. And we do that by measuring the number of infected cells that I have in the step function. So it's gonna tell me per time how many infected cells I have by measuring the length of the cell list and passing that number to the data series using the add data point method, referring to the specific CDs and using the specific variable. So now I can save my simulation. Previously, I had commented out the number of infected cells in the from the ODE. Now I want to uncomment it to be able to compare it. So I select the data where I'm adding the data series, the data points from the ODE, and I come to edit, and I hit log uncomment, and now that data series is gonna be, those data points are gonna be back in my plot window. Now I can come back to CompuCell and when we look at the plots, we can see that we're plotting both the uninfected and the infected types, both in the ODE and the cellular version. And the colors in this scheme correspond to the same colors in the plot. So blue are uninfected, red are infected, and green are virus releasing. So we can see how the two curves track each other, and we can confidently say that any deviation from the curves must be associated to the fact that I have discrete number of cells in CompuCell, whereas I have continuous number of cells in the ODEs. Okay. So I think what I had next was an exercise for you guys to implement on your own the transition from releasing to dead. So what I'm gonna do is, because we're about to finish, I'm gonna stop here, and I'm gonna leave that as a homework, and then tomorrow we can come back to implement to finish implementing the transitions between epithelial cells, and then we can talk about how to continue cellularizing this model. What I'm gonna do is that I'm gonna download this specific version that I've been working on, the one I just stopped working on. I'm gonna upload it to Google Drive as it's gonna be called homework 2.1.1. So that's gonna be the version of that's gonna be the code. So you can guys start from here and then add the remaining transitions based on the discussions that we had. I do have a question. How many people were able to actually implement at least one or two of these transitions? Let's see. Okay. Oh, okay. So some people, yeah, right. Some people are a little bit ahead. That's okay. That's totally fine. Some people are following. If I'm gonna share this code, the code as I'm stopping at right now, so people who were not able to complete the transitions up until this point, I'll be able to review the code as I implemented it and then build up from that one for tomorrow.